So today we'll be covering capacitors. Capacitors are seen in almost every single electronic device that we have. From our phone to our fridges to our watches, capacitors are in almost every single component of our lives. Have you ever wondered how a camera charge or a camera flash charges up before taking a picture? Or how your computer's memory turns on and off at will? Well, capacitors are at the core of this concept. So we're going to introduce capacitors as a key component of electronics and understand what actually defines capacitance. What are some of the individual formulas and units that we need to know, and then solve two example problems to get an understanding of how we can actually use the formulas and concepts that we've learned thus far. So let's get into our lesson on what is an actual capacitor. A capacitor is an electronic device that specifically holds charge in the form, or that stores energy in the form of electric charge and electric field. Therefore, a capacitor is an electronic component that stores energy in an electric field between two conducting plates. This charge that specifically builds up on those two parallel plates and the electric field between those two the electric field between those two plates is specifically how we can get the charge to stay within the capacitor. There's a couple of important formulas that we need to look at as well. The fundamental formula that we have to look at is the formula C equals Q over V, where C is the capacitance measured in farads, F. Q, as we've already seen, is charge, and that is measured in coulombs. And then finally, V is measured in volts, or the voltage across the actual parallel plates. These three variables are what fundamentally determine how much capacitance a capacitor or a parallel plate system specifically has. On the right here in the diagonal is what a parallel plate capacitor specifically looks like. There's two parallel plates, and when you attach wires to these and connect it to a voltage, you're going to have one parallel plate with positive charge and the other parallel plate with negative charge. Therefore, this one is going to be positive, and this one is going to be negative. In between the space of the parallel plates, we have something known as a dielectric. A dielectric is a type of material where if you put it into a capacitor, the charge holding capabilities of that capacitor increase greatly. So if you want a super efficient capacitor that holds a lot of charge, you need to put in a capacitor. Therefore, when you do put in that capacitor, the capacitance and the whole dynamics of the charge storing nature of the capacitor will change, meaning that the equation will also change with it as well. If we look at that formula is now C is equal to epsilon times A over D, where C is, of course, going to be the capacitance once again. Epsilon is the permittivity of the dielectric. A is the plate area of parallel plates. And D is going to be the distance of plate separation. So, in our dumbed down example in the top right, we can assume that this distance right here is going to be d. And if we multiply this width by this height, we get width, height. We have W times H is going to be equal to A, which is exactly this value. Now, this value of permittivity right here is going to be a constant that comes with the type of dielectric. For example, if you're using a dielectric of a certain material, that material is going to have a specific permittivity, which will be given to you in any single problem. Likewise, if there is free air within the parallel plate capacitor, the permittivity of free air or of a vacuum is also completely different than that of a dielectric being stuck into that spot. So now that we've understood a little bit what is a parallel plate capacitor, how do we really calculate and know the energy that's stored in a capacitor? As a little bit of a recap, the amount of energy that's stored is based on the electric field and the strength of the electric field. However, that electric field is also dependent on several other different factors such as dielectric, area, distance, the voltage that's actually applied. We can simplify these relationships into a few critical variables. Let's look at the formula. U is equal to 1 half CV squared, where U is going to be the energy in joules. C, as we obviously know, is capacitance. And V, as we know, is the voltage applied to capacitor. Therefore, if we really study some of these terms, we can see that as the capacitance of the parallel plate capacitor increases, this linearly changes the energy that can be stored in the parallel plate capacitor. Likewise, if we start increasing the voltage that's applied to the capacitor, the energy that we can store is going to increase at a square rate because of this square term right here. Let's take a look at a couple of examples and really see how we can apply some of the formulas that we've understood so far. So this is a pretty easy example right here. We have a 5 microfarad capacitor. Most capacitors are typically in the microfarad range. Now this capacitor is connected to a 12-volt battery, meaning that the voltage across the parallel plate of the capacitor is going to be 12 volts, as we know. We need to calculate how much charge is specifically stored on the capacitor. So what are the equations that we know and what is really relevant in this case? We know the capacitance, we know what C is, we know voltage, we can check that off, and we need to know what is the charge. What is an equation that really has all those relationships? It is Q equals C times V, an equation that we've already studied. Since we have all the variables here in place, we can simply plug and chug into our equation. Q is equal to 5 microfarads multiplied by 12 volts is going to equal 6 times 10 to the negative fifth coulombs of charge on this capacitor. That is simply our answer. Let's look at another example. This is going to be a slightly more challenging example since we have 3 capacitors in this case, and we're doing a little bit of a different type of calculation. When we have capacitors within a circuit, there's going to be often times when we have to put those in series and parallel combinations, exactly how a resistor network would really work. In this case, we have 2 capacitors, a 6 microfarad and a 3 microfarad capacitor in parallel with each other and that combination being in series with a 2 microfarad capacitor. What is the total capacitance of this network? In this case, What we have to know is series versus parallel. It's often easier to look at the parallel situation in this case. If we have several parallel capacitors, let's call them C1, C2, C3, the equivalent capacitance is going to be equal to C1 plus C2 plus C3 dot 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 until you finish all those parallel capacitors. Likewise, when you're looking at series capacitors, 1 over the equivalent capacitance is equal to 1 over C1 plus 1 over C2 plus dot dot dot. So it's very similar to how we actually calculate the equivalent resistances of series and parallel circuits. However, in this case, it is exactly flipped. The way you calculate series resistances is the same as calculating parallel capacitances, and the way you calculate parallel capacitances is the same, or the way you calculate parallel resistances is equal to how you calculate series capacitances. Let's use these rules to calculate what is the total capacitance of this network. In this case, it's likely going to be a little easier to do the parallel capacitances first. So if we do C parallel, this is going to be equal to C1 plus C2. We can plug in our values here of 6 microfarads plus 3 microfarads equals 9 microfarads. Now we can just add that 2 microfarad capacitor into this 9 microfarad equivalent capacitance. Therefore, C total is going to be equal to, and mind you, this is 1 over C total technically. It is going to be 1 over 9 microfarads plus 1 over 2 microfarads. Therefore, if we put this all into a calculator and solve it all out, the value C total is going to be equal to 1 over 0.611 or 1.64 microfarads. This is our final answer, and this is what the total capacitance of the network is going to look like. So let's wrap up and really understood what we've learned so far. Capacitors are circuit elements specifically used to hold charge within their electric field. If we apply a dielectric within that capacitor, the capacitor or the overall capacitance of the parallel plate capacitor is going to increase significantly via the equation C is equal to epsilon A over D, where A is the area, D is the separation between the plates, and epsilon is the permittivity of the dielectric. Where exactly can we apply this knowledge? Where can we see capacitors specifically? Some specific applications include power systems filtering, especially when we want to get rid of ripples and discrepancies within power. Capacitors are a fantastic way that we can install into different types of power lines. You can also use it within energy storage, the most obvious way to look at it, storage. And this can be used in camera flashes, as I mentioned, defibrillators, power backups, a number of different sort of ways, and this is by far the most important application of a capacitor. Where are we really going with this information? Why is it important that we need to know capacitors? Well, capacitors are extremely important because they are prevalent in all types of electronic devices. In any type of device that you see, as I mentioned, whether it be monitors, keyboards, laptops, anything, capacitors are going to be at play because of the energy storage capability that they always have. There's also, and this is going to be a lead up into a further topic, a an application for AC power. and filtering. AC power is obviously what comes out of all of our wall outlets, and capacitors are a critical component of that system. So, today we've covered a lot of information on capacitors. If you want more information and tutoring, visit us at voltagelearning.com and feel free to like, comment, and subscribe if you want more of this information. Until next time, we'll see you guys later.